everywhere. Today's goal of this lecture. Today I will see some question. Just as a review, today I will see reducibility of polynomial and irreducibility of a polynomial, just as a review. Till long day after, today I will discuss ring theory, just as a review. Today I will discuss some question about the idea of reducible polynomial and irreducible polynomial. Okay, first question. Let fx equal to x square plus x plus 1 and gx equal to x square plus x minus 2 be a polynomial in zx. Then which of the following statements are true? Option 1. For all prime number p, fx modulo p is irreducible in z mod pz. Option 2. There exists a prime number p such that gx, here gx is this polynomial, gx modulo p is irreducible in z mod pz. Okay. Option 3. Gx is irreducible in qx, and option 4. Fx is irreducible in qx. Fx equal to x square plus x plus 1. We all of us know this polynomial has a root in complex number. It has a complex root, and gx, notice g1 is always 1 plus 1 minus 2, that means this value is 0. That means at the point 1, gx always has a root. So, notice at first option 1. Option 1, for all prime p, fx modulo p is irreducible in z mod pz. Here I will use the mod p irreducibility test is, let p be a prime number, suppose that fx belongs to zx and degree of fx greater than equal to 1. Let f bar be the polynomial in Zp obtained from fx by the reducing all coefficient of fx of modulo p, and if f bar is irreducible over Zp and degree of f bar by reducing degree of f bar equal to degree of f, then fx is irreducible over q. Notice here fx equal to x square plus x plus 1 and over z3 f bar would be also, it would be reduces, after reducing it also would be this over z3 f bar 1 equal to 1 plus 1 plus 1, and this is equal to 3, which is congruent to 0 in modulo 3. So, for all prime p, fx modulo p is irreducible in z mod px. This is not true. For the prime p equal to 3, fx has a root. So, option 1 is a wrong option. Option 2, there exists a prime number p such that gx modulo p is irreducible in z mod pz. Since it has a root, gx has a root at the point 1, so this is also not true. Option 3, gx is irreducible in qx. This is also not true, because since at the g1 equal to 0, that means it cannot be. It always has a root, at the point 1. And option 4, fx is irreducible in qx. We all of us know let f be field and fx is in fx and degree of fx is of 2 or 3. Then fx is reducible over f if fx has a 0 in f. If fx has a 0 in the field, then always fx is reducible over f. Since q is a field and here f is second degree polynomial and its root always belongs to complex number. So it has no root in qx. So fx is irreducible in qx. This is be the right option. I hope my all viewers have understood. Okay? Oh well. Next question. Which had come session net December 2024 exam? The question is qx modulo x to the power 6 plus x to the power 5 plus x to the power 4 plus x cube plus x square plus x plus 1. Is this quotient ring is isomorphic to field? We all of us know this theorem. If f is a field and px belongs to fx is non-constant polynomial, then fx modulo ideal generated by px is field if and only px is irreducible polynomial over the field. And here fx equal to 1 plus x square up to x to the power p minus 1 and f is irreducible over q when p is a prime number. Then fx is irreducible over the field z. Here qx modulo x to the power 6 plus x to the power 4 plus x to the power 4 plus x cube plus x square plus x plus 1. Notice here qx modulo x to the power 6 plus x to the power 4 plus x to the power 4 x to the power 5 plus x to the power 4 plus x cube plus x square plus x plus 1. Notice this is the cyclotomic polynomial and this cyclotomic polynomial is irreducible over q. We all of us know this is look like cyclotomic polynomial and this cyclotomic polynomial is irreducible over q when p is a prime number. Here p equal to 5. This is the prime number. So since this is the irreducible polynomial and q is a field, so obviously this is isomorphic to a field. So option 1 is a right option. Option 2 qx modulo x to the power 5 plus x to the power 4 plus x cube plus x square plus x plus 1. Notice here p equal to 6, which is not prime number. So f is not irreducible over q. Here notice f of minus 1 equal to 0. So since f of minus 1 equal to 0, so here we can write this polynomial, if we consider this polynomial as px, then we can write px equal to x plus 1 times qx. Obviously degree of qx is less than equal to 4. Since this is look like this is look like the reducible polynomial. So qx modulo x plus 1 times qx is isomorphic to, this is not isomorphic to a field. So obviously option 2 is not correct option. And option 3, zx modulo x minus 101. Since z is not PID, since z is a not field, so zx is not PID. And we all of us know x modulo ideal generated by x minus m, this is isomorphic to z, and z is integral domain, not field. So this is not be a field, isomorphic to field. And option 4, qx modulo x to the power 43 minus 41x plus 41. Here notice px equal to x to the power 43 minus 41x plus 41. Here use the Einstein's irreducibility criteria. Just review Einstein's irreducibility criteria. Fx equal to a naught plus a1x plus a2x square up to an x to the power n. For some prime number p, if p divide a naught, p divide a1, p divide a2, but p does not divide an and p square does not divide a naught, then we can tell fx is irreducible over q. And if GCD of a naught up to an equal to 1, then we can tell also fx is irreducible over z. Okay. Consider p equal to 41 and notice 41 divide minus 41, also 41 divide 1, but 41 square, sorry 41 does not divide 1, also here a naught is 41, 41 square does not divide a naught, this means 41, and 41 divide a naught, here a naught means 41, 41 divide 41, but 41 square, p square does not divide a naught. Therefore, fx is irreducible over q. Okay. Therefore, by Einstein criteria, we can tell this is also isomorphic to a field. So, option 4 also right option. I hope my all viewers have understood this is easily. Okay, OL. Next question. Which of the following polynomials are irreducible in ZX? Option 1, x to the power 4 plus 10x plus 5. Here use the mod p irreducibility test. Consider p equal to 5. 5 divide 10, 5 divide 5, but 5 does not divide 1, and 5 square does not divide 5. So mod p, by mod p irreducibility test, this is irreducible in Q, and since GCD of 1 comma, the coefficient 1 comma 10 comma 5 is 1, so this function is irreducible in QX, also ZX. Option 1 is the right option. Second, x এর কিউব minus 2x plus 1. fx equal to x এর কিউব minus 2x plus 1. Here, root test is let fx equal to a0 plus a1x plus a2x square up to an x to the power n be a polynomial with integer coefficient with an not equal to 0. And alpha equal to p over q is a root of fx, where this p is an integer factor of the constant term a0 and q is a integer factor of the leading term an, and we have to find if alpha equal to p over q, if this is the root of fx, then by rational root test we can tell fx is reducible. fx is reducible over q. If there exists no root, then we can tell fx is irreducible over q. Here I will use the rational root test. Here alpha equal to p over q, where p is the integer factor of constant term a0, here a0 equal to 1, and the factor of 1 is plus minus 1, and q equal to integer factor of the highest coefficient, here also 1, that means p equal to plus minus 1 and q equal to plus minus 1. Therefore, p over q 1 over 1, at first check at this point, this is equal to 1, and f of 1 equal to, notice 1 minus 2 plus 1, this is equal to 0. Since at the point 1 has a root, so by rational root test we can tell this polynomial is reducible in qx by rational root test. And since GCD of 1, 2, 1 equal to 1, since this polynomial is primitive polynomial, so that implies this is reducible in qx also. So option 2 is a wrong option. And option 3, x to the power fx equal to x to the power 4 plus x square plus 1. Here this is the fourth degree polynomial, so we can write this polynomial as this ax square plus bx plus c times dx square plus ex plus f. Okay, and since the coefficient of x to the power 4 is 1, so a would be 1. Also constant term is 1, so c and f would be 1. So this polynomial would be such type x square plus bx plus 1 times x square plus ex plus 1. Here what would be the value of bx and b and e? This is the question. Notice if you put b equal to 1, then this would be x square plus x plus 1, and if you put e equal to minus 1, then this would be x square minus x plus 1. Okay, therefore fx we can write this as product of two irreducible polynomial. So fx is also reducible polynomial. Next, fx equal to x এর cube plus x plus 1. Here also use the rational root test. Here p equal to 1 and q plus minus 1 and q equal to plus minus 1, and p over q equal to 1. At the point f of 1 equal to 1 plus 1 plus 1, 3, which is not equal to 0. Also f of minus 1 equal to minus 1 plus 1 plus o. Minus 1 plus 1. This value also minus 2 plus 1 minus 1. This is not equal to 0. So, these polynomials, since alpha equal to p over q, at this point the function has no root. So, the polynomial x cube plus x plus 1 is irreducible in zx. Because here it is actually irreducible in qx, since GCD of 1, 1, 1 equal to 1. So, this is irreducible in zx. I hope my all viewers have understood this type of question. Okay? Oh well. Today I will stop here. In my next video, I will discuss different type of question about ring theory. Actually, this topic is very important for competitive exam. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.